welcome everyone to this new appointment of the GGI Tea Breaks. As you see, we are again in our rooms because we are trying to set a problem with the audio in the GGI room, and it will be settled, I hope, very soon. Anyway, the workshop at the GGI is going on, and as I told you, we are really happy to start again the in-person activities. Today we have another very, very interesting colloquium, and let me call Alessandro to introduce the speaker.
Hi everyone, thank you Stefania. So it's a great pleasure to introduce today's speaker, who is Subir Sachdev. Subir is a professor at Harvard University and is currently a visitor at the Institute for Advanced Study in Princeton. And he is one of the world leading experts in condensed matter physics. He received a number of prizes and awards for his work, including the Larson-Sager Prize from the American Physical Society and the Dirac Medal from ICTP. And this work over the years explores several properties of quantum phases of matters and quantum materials, but lately also had some very interesting connections with what we would normally regard as high energy physics or gravitational physics, such as black hole physics. And this indeed will be the topic of today's colloquium. So without further ado, please, Subir, take the floor.
Okay, thank you very much, Stefania and Alessandro, for the invitation to give this colloquium. I'm very happy to talk to what I understand is people from different fields of physics. As Alessandro said, I'm primarily a condensed matter physicist, and the problem of Planckian metals, which I will introduce very shortly, is something that has dominated the field for many years, and there's been some recent progress. And surprisingly, the tools that are making progress in the study of Planckian metals are also the tools that are behind some advances in recent years in understanding the black hole information problem. So my expertise, if any, is certainly in the first part, but I will try to give you my own view of both problems. Okay, so let me begin by introducing Planckian metals, and then I'll introduce black holes, and finally, the main set of ideas belong to what's called the SYK model, and then I'll show you how insights from the solution of this model are leading to progress in two very different fields of physics. Okay, so let's talk about Planckian metals, but before we get there, what's ordinary metal, like steel or copper or aluminum or something? Well, the basic feature of these metals is that you have electrons that move through the entire crystal, and that leads to conduction of heat and electricity. But now these electrons interact with each other, but it turns out the interactions are such that you can think of the electrons as quasi-electrons. They're almost particle-like with a little cloud of other excitations around them, but that object, the quasi-object, behaves just like a particle. And so you have the quasi-particle picture, which is then behind really the entire theory of metals and insulators and superconductors and semiconductors, and very, very successful theory. And what makes it very successful is that these quasi-objects, as they move along, it takes a while before they really feel each other's presence, and there's some scattering time, which in some sense is very long. And it's not difficult to see that the whole theory is self-consistent, provided this time is longer than a fundamental time, which just made out of fundamental constant of nature, which is what we'll call the Planckian time, which is Planck's constant divided by temperature in units of energy. Okay, so this is required that the scattering time be much longer than the Planckian time for the quasi-particle picture to make any sense at all. And from another perspective, you can think of these systems as, almost integrable, because there are these electrons that are quasi-particles that are moving around ballistically for quite a while at low temperatures. And then only after they have lots of collisions do you get true chaos setting in. And it's those collisions that are responsible for the resistivity of the metal. Okay, but then now let's jump ahead to the high temperature superconductors. This is the famous phase diagram of one of them as a function of hole concentration and temperature. For the moment, I don't need to know anything about the details of the structure of these materials. I just point out that there's been many, many experiments that have been focused on this regime here, which is above somewhat higher temperatures, let's say 150 Kelvin or 100 Kelvin and above. This is still a very low temperature on any microscopic energy scale, although it's above the superconducting critical temperature. And unlike ordinary superconductors, low temperature superconductors like aluminum, when you're in this region, it doesn't look like the quasiparticle picture is working. So this is what people are calling the Planckian metal. And one reason they call it the Planckian metal is that if you try to make some estimates of this scattering time, and I won't go into the details of how the experimentalists do it. This is one particular table from a recent, not so fairly recent paper on many different materials in the same class. And they measure the 1/tau, and they find to high accuracy, it's actually a linear function of temperature. And this coefficient alpha is very close to 1. Okay. So this immediately tells you that whatever is happening in these metals, including in these high temperature superconductors, it's the quasi-particle picture is not working. And so really the key question is, can we develop a theory for electrical transport in a material without quasi-particle? That's the question that's involved many of us in the field for many years, and I'll tell you about some recent progress. It's turned out to be a very difficult problem because you can't think in terms of these particle-like objects moving the current. So then the question becomes, what is actually moving the current, and how do these very messy interactions interact with each other? Okay. All right, so here's another, just a very recent experiment, just published in Nature, where they've used a somewhat different method to measure the scattering time. And in this case, they can distinguish the scattering time of electrons going along different directions. And what they find is that there's an isotropic piece, which doesn't depend on any of the details of the lattice structure. And if you look at this isotropic piece, here's its temperature dependence, 1/tau, again, linear function of temperature with alpha close to 1. So that's really quite amazing because these different materials I've shown you have very different natural energy scales by order of magnitude, but yet this time is just given by temperature. The natural energy scale of the interaction doesn't seem to appear at all, which seems very counterintuitive because in the quasi-particle theory, the scattering time is entirely dependent on the strength of the interactions. So there's some kind of scale invariance, which suggests that you should be looking at some scale invariance, state of matter, and that will play an important role in my discussion. All right, so then, just from these experiments, there's, all kinds of very important questions that are mostly, on which we've been working. We need a theory for a fermion system with variable density with quasiparticles and a relaxation time over h⁴kt. And in fact, we had no such theory, and now we at least have a theory. It's still a theory of a system that's very different from the experiments, but that's still very useful, and that's what I'll talk about. And then once you have such a theory, then you have to actually compute something like a resistivity and show that the resistivity has the same scattering time. And then finally, of course, once you've understood this metal, the hope is that you can then understand how this metal gives way to the superconductor. After all, there's nothing more important than computing the value of Tc. But I feel there's no way you can do that unless you understand where you're coming from, what the pre-superconducting state is. So that's really why this is a really key problem. No one's going to predict high temperature superconductivity unless they understand the Planckian metal, at least in this class of materials. All right, so that's a quick summary of the basic central problem of people studying high temperature superconductivity and many related correlated electron compounds. I mean, this kind of behavior is present actually in many compounds, including recently a number of experiments on twisted bilayer graphene. Okay, so, but I'm going to jump ahead to a completely different set of problems and give you a very quick introduction to black holes. And initially, this seems totally crazy that there could be any connection between these two problems, but hopefully you will be convinced by many of the things I'm going to say later. All right, so what's a black hole? Well, a black hole is, you need a theory of gravity, it's Einstein's theory of gravity. And Einstein's theory tells us that if you have a black hole if you have a sufficiently dense piece of matter of mass m, and if its radius is smaller than this horizon radius, then that portion of space inside the horizon is disconnected from the rest of the universe, and light itself cannot escape from this black region. Of course, this has to be very, very dense. If you took the Earth's mass and this so-called radius, the Schwarzschild radius, is only 9 millimeters. So you'd have to compress the Earth to a radius of 9 millimeters. But of course, there are out there in the universe, now we know today, many, many black holes, including one at the center of essentially every galaxy. All right, so now what I want to think about are quantum black holes. And this subject started with the work of Bekenstein and Hawking in the 70s. And what they concluded was that once you apply quantum mechanics to black holes, they're not just completely, objects just totally black, that nothing ever comes out of them. They actually are like a black body, which is radiating at like has a temperature. And in fact, just like any other black body, there's also some quantum degrees of freedom associated with every black hole. So they computed the entropy and the temperature through some semi-classical arguments that I won't go through. But roughly speaking, what they were looking at was the entanglement of EPR pairs, one outside the black hole and one inside the black hole, and the entanglement entropy of those quantum degrees of freedom can go across a black hole horizon, because after all, entanglement doesn't really live in any region of space. So another thing they found was that the entropy is proportional to the surface area. So they gave an expression for the entropy and also the temperature, called the Hawking temperature, in terms of the mass of the black hole. Okay, now there's many shocking things about these formula. First is simply the fact that the entropy is a finite number, because if you take quantum field theory of electromagnetism, entropy is not finite. It depends on some cutoff. It's a very UV ultraviolet sensitive quantity. But once you take a theory of gravity, it seems entropy is finite. And not only is it finite, it's not proportional to the volume. It's proportional to the surface area. This you can somewhat understand from ideas on entanglement entropy, but it suggests a picture, which I guess probably due to John Wheeler, that we should think of a black hole as a bunch of qubits, with the qubits living on the surface of the black hole. And the number of these qubits is equal to the entropy of the black hole. So that's why it's proportional to the surface area, why the qubits are necessary. So this is a very crude picture, but the question is it really correct? We don't know for sure, but one really, to be able to put these results of Hawking and Bekenstein on a firm footing, we do have to come up with some understanding of what are the quantum degrees of freedom that are leading to these strange features. Another interesting property of black hole. So now we have decided a black hole is actually a black body at some temperature. So then you can ask, suppose I perturb a black hole, how long does it take to relax? So this was a question answered by Vishveshwarov, actually even before Bekenstein and Hawking, and he found this answer, that there's a black hole quasi-normal modes, and the black hole will relax quite rapidly in this time. Well, what is this time? Now that we have an expression for the Hawking's temperature, you find that remarkably this time is exactly h power over kth, the Planckian time, amazingly. So a black hole also has a Planckian time relaxation like a strange metal. So that, at least in my own work in this topic was the first hint that there's a connection, that the same time appears and it takes for the system to relax, a system without quasiparticles and a black hole. So there's a connection between the two. Here, I just want to mention this paper recently, which took the LIGO data, or LIGO-Virgo data, I should say, and measured, some kind of merger time, some kind of time it takes for these two black holes to become a single black hole. And that time, in fact, agrees with the calculation, is around h⁻/kT. So, in the past year, there have been two very different papers. One is this paper here, seeing universality of h⁻/kT in black holes. And there's this paper here, seeing universality, the same universality in a Planckian metal. Okay, so that's quite amusing, at the very least. Okay, but is there a connection? And my point is that in fact there is. Okay, so let me give you some idea of, one way of the black hole entropy has been computed. I think it would be too much to say it's all understood. So if I didn't know anything, what I would say is, okay, I have a classical action, which is Einstein gravity and Maxwell's theory of electromagnetism. And Feynman tells us you take the classical action, put a 1/h⁻ in front of it, and then you compute the path integral. We integrate over all the metrics of space-time and the electromagnetic field. Okay, so let's try to do this in the case when you have some matter that's collapsed into a black hole. So in general, this is a totally hopeless task because there's all kinds of divergences and you can't make any sense of it. But there was quite an amazing calculation by Gibbons and Hawking, which actually said, well, let's not worry too much. Let's just evaluate this action at the saddle point. So we just look at the saddle point equation here, compute the action, and that will give us some approximation to the quantum physics after we put the 1/h⁻ down here. Okay, so this was done by Gibbons and Hawking in sort of the Euclidean time geometry, where the length of the time circle is h⁻ divided by temperature. And so you get actually a well-defined answer. And for a black hole with a charge, net charge Q, which I'm going to consider because it simplifies things in what I'm interested in, you find that as the Hawking temperature goes to 0, indeed there's a black hole entropy. This is the Hawking formula where A of T is the area of the horizon. And you can derive this from this calculation, which, apart from some subtleties with boundary conditions, is in the end not much more than saddle point of the action. And as temperature goes to 0, you get some overall constant. A0 is the area of the horizon at 0 temperature. And then there's some correction, which is linear in temperature, where A0 is a function of Q. So this is something you can, after some work, read off from these two papers. Okay, and there's a 1/g here, which is Newton's constant, and an h⁻ too. Okay, so that's the result you get, but that's just from the value of this constant. And well, this is okay, that's very nice, but that still doesn't answer the question of what are the corrections. You still have to do the path integral about the saddle point. All right, so now there's some questions, should we believe this? Can we compute the corrections to this entropy in the semiclassical Einstein-Maxwell theory? And the answer I'm going to argue is in fact, yes, we can. The fleeting correction you can get. And then once you've computed it, can this entropy be understood in this picture here? Is it really that of some qubits with a discrete spectrum? It turns out that the first correction is insensitive to exactly what's going on at very high energies. It could be string theory or whatever. But there are some choices where you can in fact see the answer to this is yes. And that's really the main thing I'm going to show you today. There are more subtle questions, what happens to the black hole as it evaporates? How does the entropy evolve? And can you still divide the evaporation by a unitary quantum system using a bunch of qubits? I don't think that question's been answered completely today, but there's been a lot of remarkable progress, which I won't talk about. But it's progress using tools very closely related to the ones that I'll discuss. Okay. All right. So I've given you then introduction to two, central problems in two different fields of physics, which have been around for a while, and I'm going to argue that finally we're making a little bit of progress on these long-standing problems, and at least some of that progress relies on having a solvable model. So it's always nice in physics to have a model that you can solve completely, and you can solve this almost completely of a system that looks like parts 1 and 2. And from my perspective, what's unique about the SYK model, it's a solvable model which has no quasiparticles. You can still understand a lot about it. So it's a model with, another way of saying, a very strong quantum chaos. In fact, it has maximal chaos in some recent definitions, but it's still solvable, and that's what I want to introduce. But before I introduce the solvable model, let me introduce this model without quasiparticle. Let me just take a very simple model with quasiparticles, because then I can compare and see what's really different about it. So if I just take free fermions hopping on some random matrix, so they can hop from psi I to j with some amplitude Tij, then and I look at the spectrum of states. So I just have to diagonalize this Tij. So it's an n by n random matrix if I have n sites, and then you get some eigenvalues of a random matrix, which are now of course very well understood. The theory of what the eigenvalues of a random matrix look like. Now I have a many-body system here, so I fill the lowest. I fill the lowest NQ eigenvalues. So these are the occupied states in yellow, and then I have some Fermi level, and the density of states is the semicircle density of states, and the density of states at the Fermi level is rho 0. Okay, and the spacing between these states is 1 over n as n goes to infinity. Okay, so now if I take this system, so this is really a free quasiparticle, so it's essentially integrable because there's no interactions at all. And if I look at the many-body density of states, as I'll show you, it doesn't they don't obey eigenvalue repulsion. So in the many-body sense, it's integrable. So one of the things that you always compute in freshman solid-state physics or undergraduate stat mech is the specific heat of a free fermion system. And we know the specific heat is just given by the densities of states. And this is the famous Sommerfeld formula. Specific heat or entropy at low temperatures is the density of states times the factor of pi squared over 3 times the number of sites times temperature. So it vanishes linearly with temperature. Okay, so that's free fermions with some density of states. But now let me just take exactly that problem and plot it in somewhat a perverse way. Let me think about it as a many-body system. Okay, so I have some single particle eigenvalues epsilon alpha, which I showed you here. These are the epsilon alpha with spacing 1 over n. And then I occupy them or not occupy them. So n alpha can be 0 or 1. So the n eigenvalues epsilon alpha, I have 2 to the n states, these many-body states. And now I'm working in the grand canonical ensemble. So the many-body excitation energy EI is given by this formula. So all I do is compute all 2 to the n values of EI for a 16 by 16 matrix or something. And these are all the eigenvalues, the capital EI. So this is the density of states, D of E, of the many-body eigenvalues. So what is the density of states at low energies over here? So the density of states, well, that's just the exponential of the entropy. That's the definition of the entropy. And I just told you the entropy in the canonical ensemble is, well, grand canonical ensemble, sorry, was n gamma t. So now I want to convert that to an entropy in the microcanonical ensemble, S of E. And if you just do that conversion, this is what you get. It's 2n gamma E, where E is the energy above the ground state, total energy. So the total energy of the ground state on any typical state is proportional to n. So this whole thing is e to the n. So there's an exponentially large density of states. Now, initially, that might seem kind of surprising, but the point is that the single particle states have spacing 1 over n. But if I now take the sum of single particle energies, if I pick one energy, then by accident, there'll be some other set of occupied state which is exponentially close to it in general. There has to be, just by thinking of the bandwidth and the total number of states. Okay, so that's, again, freshman physics presented in a somewhat unfamiliar way. Okay, but now let me look at these states and just go all the way down to very low energies at the bottom of the band. So here, the density states become very small. There seems to be a tail. And here are the individual levels. So what's happening here? So at the very bottom, something different is happening. If I go back to this picture, the ground state is the yellow regions occupied. What's the first excited state? Well, the first excited state is when maybe I occupy that state or I empty that state. And that costs me an energy 1 over n. So these states, as you can see from this picture, are much farther apart at the bottom of the band than they're in the middle of the band. In the middle of the band, the density of states was, the spacing was e to the minus n, because the exponentially large entropy is proportional to n. Whereas the bottom of the band, it's not e to the minus n, it's just 1 over n. So the density of states, instead of being e to the n, becomes n. And this is basically evidence that in the system that there are quasiparticles. All right, so now let me take a many-body system where I will numerically compute, but this is a lot of it has been done analytically, the many-body density of states. In fact, in this problem, I cannot even define the single particle density of states because it's a strongly interacting problem. So here's the Hamiltonian of the SYK model. It's characterized by a set of random numbers, u alpha, beta, gamma, delta, which determine a two-body interaction. So let me just show you a pictorial view of it. So you have n sites. These could be different orbitals or sites or whatever. And some fraction of these are occupied by the electrons. And then you have some interaction matrix element, which can entangle these electrons. So for example, these two electrons can interact with each other and hop to those two sites. And associated with that process is some number, the u alpha, beta, gamma, delta. And similarly for any pair, if you pick any pair, they can hop to any other site. Of course, you have to obey the exclusion principle. All right, so there's order n to the 4th possibilities, n to the 4 matrix elements that you have to choose to define the model. Okay. And now the remarkable thing is that if I gave you a set of numbers and ask you to solve this problem and get me the eigenvalues of that problem, you can't do it. But if I just tell you these numbers are random numbers and give me some average properties, then you can do it. And that is what we did in 93 for a slightly different problem. And now, of course, much more is understood. But remarkably, the average solution gives you almost all the information you want, because this problem is extremely well self-averaging. You only need one sample with n sites, and because there's 2 to the n states here, which is an unbelievably large number, it doesn't matter which random numbers you pick. Any set of random numbers will have essentially the same properties to high accuracy. In fact, exponential accuracies for some issues, some problems, some quantities. Anyway, so therefore, that's the beauty of it. There's so much chaos and there's so many different states that you can just average and get the answer. Okay, so here I show you some numerical results of the many-body density of states. Now this is a system that's much, much more complicated, and this is what it looks like. So if you look at the density of states, somewhere not too low in energy, but the energy is extensive, then this is what you find. Now for the free electrons, you had this square root of NE number, and this is exactly what you get here. But now you get the surprise, and this is what was first deduced in this paper with George and Parcolet, you find that there's an entropy as the temperature goes to 0. So there's a correction here, which tells us that even as the energy goes to the ground state, there's an exponentially large term. This was not present. S0 was 0 for the free electron problem. Now, that might seem like you're violating the third law of thermodynamics. How can there be an exponentially large ground state set of levels? But the point is, this is not a ground state degeneracy. It's a 0 temperature entropy. There is no degeneracy. So here's the actual energy levels. There's no degeneracy at all, as you can see from my exact diagonalization of one set. But if you look at the density of states of this thing, now this has been computed, it's e to the n s naught. So the key point is the following. In the middle of the band here, when the energy is extensive, the energy level spacing is e to the minus n. That's true in both problems I've showed you, the free particle problem and the interacting particle problem. However, at the bottom of the band, in the free particle problem, I had a very low density of states because I had a tail here. So here's a picture, I think. There's this tail. So this tail is not present here. Whoops, here, there's no tail. And the density of states here is still exponentially large, meaning that the n level spacing remains e to the minus n, just as it is at higher energies. And that immediately tells you there's no way there's a quasiparticle decomposition. And that means I cannot think of these states as small corrections to each other. So here, what happened was I had the ground state. Then this state was very close to the ground state, in its wave function. All I had to do in the ground state was to add a particle, but everything else remained the same. And then I made a small change here and a small change there and a small change there. So all of these states were related by very small changes to the wave function. And they ended up having, that costs a lot of energy when you make just a small change. However, here in this system, this state here, if you look at its wave function and you look at the next state, their wave functions are completely different. There's no way, they have no obvious relationship between them. And in fact, we don't understand what all these states are in any deep sense. It's just we can count them. So these very chaotic states, each with a completely different wave function, and the density of them is exponentially large. Okay, and in fact, you can compute it. And in fact, you can also compute the crossover from here to here, and it's given by this famous Cinch formula. I'll give the references in a few minutes. And then you can convert this to a correction to the entropy, because these two quantities are related by a Laplace transform, the density of states and the entropy. So if you do an inverse Laplace transform of this, you get, if you do a Laplace transform of this, you get the entropy. Okay, so there's this term here, but the correction is logarithmic. All right. Now, how was this obtained? Well, actually, this is obtained by a theory of quantum gravity. And there's a derivation of that starting from the SYK model of the theory of quantum gravity, which I will not have time to show you. But let me at least show you the corresponding calculation in black holes. So let's go to black holes. So anyway, just to summarize then, quite amazingly, to understand the density of these chaotic states at very low energies, the exponentially large density of states, you need to do a calculation in quantum gravity. And the way that happens in this case is that you start with the SYK Hamiltonian, you do a saddle point calculation. The saddle point has certain conformal invariance. And when you look at the fluctuations about the saddle point, you end up having to integrate over time reparameterizations, and that gives you the quantum gravity feature of it. All right, let me, however, turn to black holes and now apply this to black holes. And there I will at least sketch the calculation that you have to do. So let's go back to the entropy, which is, as I said, the Laplace transform of the density of states. And I told you how Gibbons and Hawking computed the entropy. They just looked at the saddle point. Now we want to do some corrections. So all right, so now in general, that's an impossible task for a generic black hole. But for charged black holes at low temperatures, it's been understood by various people. I'll give the reference in a few minutes, that in fact, you can do this, compute this correction. And it's very general, and it's just given by the semiclassical fluctuations of this theory. So why can't you compute it? Well, it depends upon, before I get there, notice that this term here, the large N result now, something that's constant plus a term linear in temperature, matches this expression here for the SYK model. And what I'm now going to show you that this correction, which comes from a theory of gravity, also matches the SYK model for a generic charged black hole, in fact, in 3 or higher dimensions at low temperatures. Okay, so note the similarity to the SYK model. Okay, so what is special about a charged black hole at low temperatures? Well, it's the geometry of the black hole. So if you solve Einstein's and Maxwell equation of a black hole of charge Q, this is in the presence of a cosmological constant, but even without it, you will find similar features. You have some kind of 4-dimensional space-time here, and this is in 3+1 dimension, far from the black hole. But as you get close to the black hole, you find that the curved geometry is 1+1 dimensional. It has a geometry of what's called ADS2, and the S2 is just the radial direction of the angular direction of the black hole. I realize I should have a picture here. So yeah, actually I do have a picture. So no, I don't. So there's a dimensional reduction from 3+1 dimension to 1+1 dimension at low energies. And the angular quantum fluctuations you can just ignore because they are much more energetic. So all of the really low energy fluctuations belong to ADS2 and its boundary. You just do have to worry about the boundary of the ADS2 region when the geometry goes from 1+1 dimensions to 3+1 dimension. Anyway, so the bottom line is that you can simplify by standard techniques in theories of gravity this path integral, which is in 3+1 dimension at low temperature, to a path integral in 1+1 dimension. So it's a theory of gravity in 1+1 dimension called the JT gravity theory. And although this could have been in principle shown by Gibbons and Hawking, it wasn't shown until recent work by Maldacena et al., who were inspired by Kitaev's work on the SYK model. Okay, so now you have a much simpler path integral, which you can be evaluated, and so when you you can actually do a further reduction, and you get an action here, which you can then turns out to be the same action that you got from the SYK model. You can start from the SYK model, get this action, or you can start from 3-dimensional gravity and get the same action at low temperatures near the horizon of a black hole. Amazing. And now you can evaluate this path integral exactly through some very clever techniques. And therefore, you get the correction of the leading low temperature correction to this entropy. This is a semi-classical correction involving actual quantum gravity fluctuation, not just the saddle point evaluation. Okay, so what do you get from there? Well, this is the correction. This is -3/2 log t is the correction to the leading term, or the Bekenstein-Hawking term. And in fact, that is exactly the correction here, which this correction here, the only thing different between them is this cutoff. There's a cutoff scale here, which is some U, which is the strength of the interactions here. And in the black hole case is determined by the mass of the black hole. So the bottom line is if you take one SYK model and for sufficiently large and you numerically compute the density of states on all the energy levels, you will get these very discrete levels. They're very hard to characterize, but you get some continuum density of states. I mean, some very dense set of levels, all discrete. Now, if you do a little bit of coarse graining and average them, you will get some function, this function here, in fact. And this has been numerically checked, you get this function. And then from this function, once you have the density of states, you can compute the entropy as a function of temperature by a Laplace transform. You'll get this answer. And this is, in fact, the entropy of a generic charged black hole at low temperature. So in some sense, what I've shown you is that once you have this correction, I've shown you that these levels here of the SYK model are one realization of these qubits. These are fermionic qubits with discrete levels, and they give you exactly the same density of states as a charged black hole at low temperatures. And in fact, we also understand why. So this one way to think about it is that you can start from these qubits and show that you get gravity emerging. So this is a theory with emergent gravity. And in fact, the gravity theory you get is the gravity theory of low energies at a charged black hole. So we have answered one of the questions that indeed there is at least one model of qubits for certain black holes, which can give you a discrete understanding of these energy levels. Now imagine some of you might say, well, what about string theory? Doesn't string theory give you an understanding of entropy of black holes using discrete quantum states? Yes, the answer is yes at a level, but it only gives you this understanding for black holes that have supersymmetry not only at high energies, but also at low energies, all the way down to the ground state. And in fact, in string theory, you get a very, very different picture of the levels. In string theory, the density of states are the so-called BPS states, and they all have exactly the same energy. There's in fact a degeneracy. And so you're kind of violating the third law of thermodynamics. There's a huge exponentially large degeneracy, which is only present because you have supersymmetry. And the degeneracy of these states is in fact matches the Bekenstein-Hawking formula. That's of course correct, but it's not generic. There's a degeneracy and then there's a gap. I'm not saying that string theory is not the answer at very high energies. It could well be the answer of theory of quantum gravity at very high energies. But we know there's no low energy supersymmetry for actual any black hole in our universe. And these string theory solutions of black holes also have low energy supersymmetry, which is not realistic. And as we see for low energy supersymmetry, the black holes have a very different structure. Okay, all right, how am I doing on time? I have about 15 minutes, is that correct? Maybe I can pause for questions before I go back to the first part of my talk, which is Planckian metals, and then conclude. If there are any burning questions on black holes, this would be a good time to ask them or put them in chat. Okay, well, then let me go back then to my safer space, which is Planckian metals, where where I actually understand the nuts and bolts a bit much better. So Planckian metals. So this is what we want to understand. What has this got to do with the SYK model, if anything? Well, at the very least, a Planckian metal is a model of electrons. I mean, the SYK model is a model of electrons where you have no quasiparticles. And the relaxation time of those quasiparticles is h bar over kT. But can we do more? Can we understand a bit better and make it more realistic? Okay, so what is a realistic model of this system? Well, the realistic model of this system is what's called the TJ model. So in this phase diagram here, you start with this antiferromagnetic insulator. So what we know in that system is that you have these electrons which sit on the vertices of a square lattice, and they're in this antiferromagnetic arrangement with half of them down and the other half up. And these electrons can exchange their spins like that. So that's has amplitude J. They keep exchanging their spins. Any pair of near neighbor electrons can exchange spin. And this system is an insulator. Now you dope it, you remove some sites, and now these particles can hop around with amplitude T. And so when you have both the T and the J processes, that's called the TJ model. So this is a very simple model, but as many people believe it has enough to describe the real physics. You don't need to worry about anything else. We would love to solve this TJ model. Okay. Well, no one's done it, but all right. That's the model we like to solve. And of course, we don't want any double occupancy. That's what makes it very complicated. So if you want to write down an actual Hamiltonian, it has a T term and a J term, spin exchange term, a hopping term, but there's a projection operator which stops you from occupying doubly occupied sites. And that's, of course, the hard part in the problem. Okay. All right, so that problem we can't solve. All right, so we, and literally there's thousands of papers doing all kinds of studies of this model, and much has been learned. I don't want to make light of it. Huge amount has been learned, but especially the strange metal has not yielded to direct analysis of this problem, the Planckian metal. All right, so we said, okay, let's solve a simpler problem. And what we're going to do is very much in the spirit of SYK. We're just going to make this Tij, the T and the J term, random numbers. So the Tij becomes random. So there's a one particle hopping, as in the first problem I told you, random matrices. And then the interaction is not quite like the U alpha beta gamma interaction. It has only 2 indices rather than 4 indices. And it's a 2-particle interaction similar to SYK because there's 4 Fermi operators here after you insert this in there. But the index structure is quite different. All right, so here's another problem we can try to solve. This is still too hard, but there's been a lot of progress in actually solving this problem over a wide range of temperature and doping, at least numerically, and also in different regimes analytically. And I could give more than one talk going to all of those, all of that progress. And in fact, I think I mentioned here, there's a review article right there, which goes through all of that in some detail, the solution of this random problem and also the non-random problem. Let me just show you some recent numerical results. So this is the kind of phase diagram you get as a function of doping and temperature. So this model, because we took random Tij, it doesn't have the superconducting phase, but we're not concerned about that. The superconducting phase is at very low temperatures. We are concerned in trying to understand what happens at higher temperatures. And what happened at higher temperatures in the real system was you had a phase here in blue, which is in fact an ordinary metal. I should have written this here, a Fermi liquid with quasiparticles. And then it gives way at near optimal doping to this Planckian metal. And amazingly, those features anyway are very faithfully captured by this random problem. So you get, in fact, a Fermi liquid here. And then if you look here, you get, transport scattering times, which again with this universality, Planckian universality, number not so far from the experiments, 1.4. And furthermore, you can also find spin-spin correlation function over this wide temperature range, which decays 1 over tau, which is exactly the behavior which is also present in the SYK model. So, which is an even further simplification of this model. So anyway, so the bottom line is that we do believe that this random Tj problem has in it a Planckian metal of just the type that's seen in the experiments. And also it's connected to SYK. So that's for progress. And there's a lot of details that I'm not showing you how all the insights of the SYK model help us understand what's going on in this random Tj model. So here, for example, is the actual presentation of the scattering time that you measure in transport. And it's linear function of temperature with a coefficient of order 1.4, and then as you change the doping, it becomes T squared. So we're coming temperature over different regimes. All right, so that's really all I have to tell you. So this, even for this part, this raises some questions. The real world is a 2 + 1 dimensional Tj model on a square lattice. Why should this random problem, which doesn't have any sense of space, because Tij and Jij are fully random numbers, the Jij part is in fact exactly like the Jij of Parisi's model, the SK model. What Parisi solved was this model here, where these are Ising variables, classical Ising, and this term is not there. So what we've done is made Parisi problem quantum, and we've added the hopping terms with fermions. That's all we've done. And the fermions being around get rid of the spin glass phase that Parisi was interested in, at least finite doping. There is a spin glass here, but I don't want to go into that. So this problem is essentially 0 + 1 dimensional because the spins and the electrons are just sitting on a fully connected cluster. just like the SK model of Parisi. So why should this zero, but there's a time direction, that's the +1. So it's a quantum problem on this cluster. Why should that have captured the physics of an actual TJ model which lives in real space? Well, I mean, in some ways you can ask that question to Parisi, and also because why should the Parisi model which lives on this cluster have anything to do with the real spin glass which lives on a lattice? And of course, we've learned it has a lot to do with it, and it's a very beautiful mean field theory. Needless to stay at this point. And I would like to argue the similar is true here. But can we say more? So why should this dimensional reduction happen? In fact, I just want to mention that this dimensional, we've already seen a version of the dimensional reduction, the gravity theory. At least if I take Einstein gravity in 3+1 dimensions, near a charged black hole with the ADS2 horizon, which is ADS2 is deep connection to SYK, it goes from 3+1 to 1+1. Now, however, can I interpret this in terms of the boundary theory sitting over here in the sense of holography? So perhaps I'm using concepts that may not be familiar to everybody here. So there's a holographic mapping of this 3+1 dimensional gravity, and it maps to a certain model which has Fermi surface coupled to gauge fields. And it's a large N model because there's lots of gauge fields around. And that problem we can now confidently say from this gravitational reduction has a dimensional reduction. So really the question is, why should this dimensional reduction, which happens for large N gauge theories, also happen in the TJ model? I don't think there's really any answer to that, but I would say the evidence from the numerics in all our studies is that it seems to indeed does happen. And I'll just leave it at that. All right, so to conclude, so the SYK model, whatever you think about its applications, it's a useful model because it's the first solvable model which has no quasiparticle excitations. And as a consequence, it exhibits very rapid thermalization and chaos in essentially the shortest possible Planckian time, and also a set of consequent scale invariant properties that eventually connect it to gravity. And the theory of the SYK model at low energy is the same of theory of quantum gravity on ADS2, appropriately interpreted. And so in the context of gravity, from these insights and connections, we've now understood that there's a -3/2 log 1/t correction to the Bekenstein-Hawking entropy of generic charged black holes. And furthermore, this entropy, including its corrections, can indeed be realized in a model that realizes these qubits, fermionic qubits. That's the SYK model. So people have taken this 2D gravity theory and pushed it much farther in a way that I don't understand the details at all, but they're all very excited, and there's been a lot of progress on the Page curve on how which describes the time evolution of the entropy of an evaporating black hole. So I'm really not the person to talk about it, but I'm sure perhaps we'll have another cloaking on those topics later. And in the context of the TJ model, it's amazing how much this random TJ model, 0+1 dimensional TJ model, captures so many aspects over a wide temperature range, including this Planckian metal behavior. Okay, thank you very much.
Thank you very much for the very nice talk. So now I would like to allow everybody to ask questions. I see already some raised hands. So what I would ask you is to please raise your hand, and then we will call you. And let's just get started. I think Eduardo Fratkin has a question, please.
Eduardo Marino was the one you, anyway, go ahead.
Oh, Eduardo.
Hello to both Eduardos, both of whom I know.
We are still distinguishable. First of all, it's great to see you, Subir.
Nice to see you, Eduardo. You can turn off your video, maybe, then I'll see you.
Well, they don't let me, okay?
Oh, okay.
And now you can if you want.
Oh, I can, okay, well, fine. I am in my office and you are not in Florence. Okay.
Hi, Eduardo.
Beautiful talk, very inspiring. Okay.
Thank you. Thank you.
Really exciting. So I have a question about the low energy part of the SYK many-body spectrum.
Yes, sure.
Okay. So this is the part where you identified that with the qubits. Now, in most
Well, that was just
no, I understand this is a qualitative argument, okay?
Well, I mean,
Yes. No, wait.
Yeah, go ahead.
Let me go to the question. So in most quantum systems, if you take a state somewhere in the middle of the spectrum, a typical state,
yeah,
will have thermal properties. For instance, the entanglement entropy of a subsystem will scale with the volume of the number of degrees of freedom in the subsystem.
Right.
Whereas states close to the edge of the spectrum typically don't. They obey an area.
Yes.
They are ground state. It seems that in this case, probably they are all thermal. Is that
correct? Yeah, I think that's.
And is this related to the question of the complexity of the states? I mean, that's what the question.
Yes, I mean, I think I would agree with everything you said. Yeah, we don't understand these states very well down here. We just know the density of them. It'd be great to have an understanding of what these states are, but it seems that all of these states, even down at the bottom, are as thermal as any other state. Yeah, they're just chaotic.
They are as chaotic, but that means
I mean, however, if I take the free particle problem, whoops, where am I? Yeah, so this is really free. So now these states are not thermal,
right?
Even though they're exponentially closely spaced. But if you turn on a little bit of interaction, they will eventually become thermal, but you have to wait a long time, right?
Yes,
you have to wait.
Correct.
So they're weakly thermal in that sense. You have to wait a long time before the chaos set in. Whereas here, all of the states become immediately thermal. That's really that's a simplifying feature in many ways.
So is there a way to quantify the statement that they are of the complexity of the states?
I would love to. I think that's an interesting question. I don't know. I mean, I would love to have better understanding of that question. Yeah.
You could imagine looking at the spectrum of Rennies and turning that into a question whether they have a multifractal character or not, for instance.
Okay, all right. I look forward to your papers on that. No, that would be
really... I'm just thinking aloud, okay? That's all. Inspired by your talk, but that's all.
Yes, thank you.
Okay,
I'm glad you liked it. And I agree with your intuition. Yeah.
Okay, thanks once again.
Thank you, Eduardo.
All right, Eduardo now again.
Hello, Eduardo. How are you?
Nice to see you.
Nice to see you.
Nice talk.
Thank you.
Subir, I have a question. It's quite easy to understand that the Planckian dissipation would lead to a linear in temperature resistivity.
Oh, I don't think so. Really? Okay. How do you do it?
Well, you put a scattering time that is inversely proportional to temperature.
Yes, but the point is that there's momentum conservation. So if you take a system without disorder, in fact, if you take any of the theories that people have talked about, where they take a Fermi surface and couple it at long wavelengths to some boson, all of those theories essentially have zero resistance.
Okay.
So really you need strong Umklapp or something. And that's, and the strong Umklapp statement is very similar to my statement of dimensional reduction. Why is Umklapp so strong is the same as the statement, why is there dimensional reduction? So that you don't have to worry about momentum conservation. I think those are related issues. Yeah.
Okay, but there is another point is how do you get, supposing you get the linear temperature dependence, but how do you get the different slopes that depend on doping?
Well, this is just numerical study. This is a numerical study of the random TJ model. We don't, we have some theory of this linear temperature dependence, and the slope is kind of a universal, non-universal number. But this is the numerical result of the
according to, it depends on doping.
Yes, yeah, these are different dopings, correct. Yeah. The overdoped side is T squared, and this is optimal doping, yeah.
Okay. Okay, thank you very much.
Sure, Eduardo.
So while other participants think of questions, and please raise your hands, maybe I will ask a small one. It's a bit naive, maybe, but you argued that even if the TJ model was two-dimensional, defined on the square lattice, then you can envision some sort of reduction by which you get this sort of 0 + 1 dimensional model. Everything is connected.
I'm just saying that there's a lot of circumstantial evidence that's what happens. I can't say I have a theory for this. I mean, I think that's
sure.
That I would say this is the central open question in the theory of Planckian matters.
But so if you instead imagine to have some other lattice, like when you have something like a lattice models, I guess you could put it on some different shape of lattices and so on, right? Would you expect that, broadly speaking, you would find a similar picture, or is it? I mean, would the notion of which lattice type you have just disappear in this sort of dimensional reduction, or would it be implemented in some? Okay. No,
the notion that it would disappear, and in a way that's good, because this Planckian behavior is seen in many different systems with different lattices, different band structures, and so on. There is kind of a super universality even in the observations. And there are theories of and if you take some particular theory of your favorite boson or your favorite quantum critical point, then it will apply to one system and not the other. So that's another virtue of this idea here, that it's actually, maybe it doesn't depend on all of that, and there is a dimensional reduction. Yeah,
I see. So it's very universal in this way.
Yeah. And this kind of idea is, Hong Liu and others have talked about it. They call it quasi-local quantum criticality and so on. I think there's something to this idea.
Okay. Thank you. So, any other questions?
I have a comment actually on what was just said. In fact, there are other materials which are not related to high temperature superconductivity.
Yeah.
That have over broad ranges of parameters, say pressure and other parameters, behaviors, essentially linear resistivity and things of that sort that can be interpreted as evidence for Planckian dissipation.
Yeah.
Those are not obviously related to any generic quantum critical point.
Right,
fact,
right.
The entire phase that is actually behaving like this.
Yeah.
So in some sense, the fact that this doesn't seem to depend on the existence of a miraculous hidden quantum critical point is actually one of the strengths of this picture.
Yes, thank you. I agree. I agree.
Because this has actually been a problem I always had with the picture of the underlying quantum critical point, that in fact that is actually much more generic than that. And
yes, this has bothered me also when I'm coming around to this point of view,
right.
Yeah, which I said others had talked about. I think, well, also I should say that this kind of dimensional reduction in a real system doesn't happen all the way down to zero temperature. I mean, eventually, let's say around 100 Kelvin, D-wave superconductivity, pseudogap, charge density waves, all kinds of other things appear, which depend on all kinds of details. But there is seems like a wide temperature regime, intermediate regime, where there is some kind of dimensional reduction. Yeah. That's certainly my view of the Planckian problem. Yeah. No. Yes.
Great. So I don't see any other question at the moment. Is there anybody that would like to ask anything? So if not, let's thank Subir again, and indeed everybody that participated in the discussion.
Thank you. Thank you.
Thank you very much for a very nice talk.
Thank you very much.